We're set to go. Thanks, Dale.
Good afternoon, everyone. Welcome to the January 2023 episode of Innovation Insights, IACMI's monthly series that highlights key members and other activities in IACMI that we think bring real value to the marketplace. Just a couple of slides before we get started. Just a reminder of what IACMI is about. We've organized around the themes of convene, connect, catalyze. We bring people together. We connect them up, and then what we hope comes out of that are things that will grow the marketplace and improve everybody's business and participation in it. Do this through a lot of activities, including networking projects, co-funding that we have available both from federal sources as well as our member sources, workforce development, which includes training, interns, education, and then we have open use facilities across the country that are unique in the United States, other expertise throughout the system, and then the opportunity to influence and consult. Just a couple of things here. I want to note that we will be at the SAMPE conference in April in Seattle. We hope you'll join us there and that you will go and become part of that event. And then the following week at JEC World in Paris, we will be there as well. We are actively at the moment planning our members meeting for this summer, June 20th to 22nd in Knoxville, Tennessee, in downtown Knoxville at the Marriott there. Here are a couple of photos on the bottom of last year's members meeting in Salt Lake City. We can't always promise rainbows, but we can ensure that you'll have a good time. So if you've missed previous episodes of Innovation Insights, they're available on our website. If you just go to iacmi.com or iacmi.org and you go to events and you go to Innovation website, Innovation Insights, you can go back to any episode and watch the whole episode, at your leisure. So lots of good content already stored there. So I'm not going to hold up our speakers. We've got three great speakers today covering additive manufacturing, graphene, novel graphene technology, and infrastructure and construction activities. So with that, I'm going to turn it over to our first speaker, who is Konstantine Fetfatsidis. Sorry about that, Konstantine, who is president of North America for 9T Labs. Really, really interesting technology for additive manufacturing. So, Konstantine, if you want to go ahead and start sharing and then unmute yourself, please join us.
Absolutely. Thank you, Dale, for the introduction. And let me get my presentation here going. Everybody see the screen, or do I need to swap display?
Yeah, you need to do the swap again.
Swap here. Is that good?
Yes.
Perfect.
All right, perfect. All right. Thank you, everybody. Good morning, good afternoon, depending on where you are all around the world. As Dale said, my name is Konstantine Fetfatsidis. Very, very nicely done there, Dale. I know it's not an easy name. So as you mentioned, 9T Labs, a company that actually spun out of ETH Zurich now 5 years ago. And just last year, the first year of some revenue generation, decided that this year we're going to expand into the North American market. And so I came on board in early October, and we've set up sort of our operations out of Massachusetts, Lowell, Massachusetts right now. And our, fundamental, product, I guess, or service that combination, I'll explain a little bit more about that, is called Additive Fusion Technology. So I'll kind of go through some of that, but as you can see, just some history here on 9T Labs. Like I said, spin out of ETH Zurich. Did a Series A last year, so in total about 22 million in funding. We now have 65 employees, majority of those, of course, out in Zurich. So growing and looking to expand, in particular, our North American operations. So, continuous fiber thermoplastic composites, we all know, many of us know anyway, have outstanding material properties, nothing new, been around for decades. They enable things like higher production volumes, lower cycle times. The part costs can be significantly lower, even though a lot of people tend to focus on raw material costs. It's important to look at the full process and consider part costs. And then, of course, as we get more and more concerned about sustainability and recyclability and greener, processes and products, thermoplastics really can address a lot of that as well. So, so with all these other, benefits like corrosion resistance, fatigue resistance, design freedom, et cetera, that you see kind of here scattered in this graphic. The main benefits of thermoplastics that have always made them sort of appealing are those that I've highlighted there on the left-hand side. However, with all that said, kind of manufacturing these small, complex parts using continuous fiber composites, so really thinking about structural parts, has really been tedious, suboptimal, a really manual process, and it really drives the part costs up. If you consider your dollars per pound on a part basis, they tend to be much higher, more complex when you factor in all the manual labor for layup, the tooling, all the post-processing required for these parts. And many times it's just kind of, the manufacturers are going to resort to metallic parts instead, aluminum, steel, titanium, mainly, right, in a lot of these structural applications. Metal remains easier to process, even simulate in FEA. And so again, as I mentioned, the expense has been the big problem. So what's lacking here is like a full stack, complete solution that takes hardware, software, and provides an automated way to make these smaller, complex parts like the geometry you're seeing there on the right, in a cost competitive way, something that can truly replace metals. I mean, we know we can replace metals from a lightweighting standpoint and cut a lot of waste as well, but can it be done so cost competitively? And that's always been sort of the challenge. And we think at 9T Labs that we can address this with our additive fusion technologies. We call it AFT, not to be confused with AFP, of course. But like I said, it's really this complete hardware software solution for affordable and sustainable manufacturing of small, complex structural parts at production volumes. So I think a lot of people, when 9T Labs started off, it started off really in a 3D printing type of technology. It was called a carbon kit. The idea was to take hobbyist 3D printers and install a little kit, be able to produce continuous fiber, to be able to do continuous fiber 3D printing. That business model has completely changed. And, I think part of the struggle here for 9T Labs, as we're looking to expand now, is kind of shedding a lot of that heritage of pure 3D printing, right? In sort of that hobbyist maker kind of community. Well, we really have become more of an industrial manufacturing solution for production quality, but also production volumes. And so as I'll explain here in a bit, with the process that we have here, this AFT process, it's not pure 3D printing, and it enables us to get really high volumes up to, even 100,000 parts a year, cost competitively. And so the workflow of AFT starts with design software. So we have our own design software called Fiberify, and that allows us to take in any kind of CAD model from your preferred CAD package. It does the topology optimization within the software for the lightweighting purposes, but then also for the proper placement of the continuous fiber, right? So this, again, necessitates an application that's structural in nature and actually requires some sort of reinforcement that the continuous fiber can do. I mean, otherwise, you're probably better off with like injection molding or something, right? So once we have this optimized geometry that we can do, the software will automatically generate, the G code and everything that drives the build module. And the build module is basically our 3D printer. But we think of our 3D printer as more of a tailored, preforming machine. It's a 2D preform system, right? And so it combines, it's a dual nozzle type of approach. Shouldn't really call it a nozzle, but the same head has the ability to print or deposit prepreg tape, thermoplastic tapes that we slit down. Right now, the standard width is 1 millimeter width, but then also can switch over to the nozzle that extrudes chopped fiber filled filaments, like in a normal FDM or FFF process. And so with that, we create, these tailored and multiple types of preforms, right? That then we can assemble this multi-assembly type of process. As you're seeing in that third box there, it's 3D printed parts. And you see when it comes off the printer, if you were to do any kind of SEM and look inside the parts, it would be pretty high porosity. 3D printing on its own, of course, is generally slow, doesn't have great accuracy. But if you're able to take those preforms and now combine it with other material formats even, right? And you're seeing examples on the bottom right box here on the Fusion module, where you have organosheets or platelets, BMC, other types of materials, and combine all that with the printed preforms in a mold, in a compression molding process. And that's what the Fusion module is, with controlled heating and cooling. Then the output, including metal inserts even, then the output is that consolidated part that you're seeing in the bottom left in the big rectangle, where you have a finished hinge. The fibers are all going in their appropriate 3D direction, right? That's another limitation of 3D printing. And then you can see the consolidation quality there too, with the very low void content, smooth surface, ready to go, really no post-processing required. And you get the benefits of compression molding in terms of volume and automation, accuracy, and then also the benefits of the 3D printing, which provide that tailorability and the continuous fiber and the steering. The two together with other low-cost materials are really what this whole AFT process is. And we sort of bring it all together with our software to have this full stack solution. So the value prop, when you use this, like I said earlier, the smaller complex parts, under 100,000 parts a year, structurally loaded, there's got to be some kind of load carrying capability here. Otherwise, probably doesn't make much sense to use continuous fiber. So we've seen a lot of really good use cases and working with a lot of OEMs and suppliers in mobility, a lot of mobility applications, whether it's ground mobility or air mobility. So bicycles are really hot, and you see some examples of parts on areas of the bikes that we've been kind of working on cars and four-wheelers and, of course, lower volume types of cars, a lot of electric stuff, scooters, e-bikes, things like that. And then aircraft interiors, right? I mean, we know that the life cycle of an aircraft can be decades, right? But the interiors tend to be replenished every, 4 to 8 years, right? And so there's a lot of opportunity there for companies always looking to go build greener aircraft cabins and kind of lightweight further and get a lot more, bang for their buck on the interior side. And so thermoplastics are gaining more and more sort of traction there, and we're working actively with different partners and OEMs and suppliers in looking at some of these applications. And altogether, the value prop here is not just weight reduction you could achieve through sort of that black aluminum, just by taking the existing design and moving it to composite, you're going to get 30% probably automatically just by doing that. We really target at minimum 50% weight reduction by leveraging that design optimization we get from our software. The zero waste is important to us too. We're really conscious about sustainability, and we're trying to say everything we do in our manufacturing process, if there's any waste generated, we try to take that, reclaim it, and reuse it. So if it's tapes, we'll chop it up, we'll use it as BMC and use it in the molding process after the fact. And then lower cost, and I think, it's not enough to just be lighter weight and reduce waste if there's also going to have to be a premium paid here. So everything we do, we work with the customer to make sure that there's a favorable business case at the end of the day as well. I should mention that the AFT process is actually an open materials platform. So while we do have strategic partners like Solvay, Arkema, Evonik, you've seen at the bottom here, some even investors, we don't limit ourselves to those materials. We offer these materials either in tape format or in filament format. But if a customer came to us and say, we really want to use, this PPS that we've qualified recently, or a bio-based, PA material, we'll work with them to make that happen. And, it's certainly compatible with our system. So earlier I kind of showed that example of the helicopter hinge. This is just kind of a nice use case, and we have more details we can share on this. It was actually a really cool video on YouTube on the Cool Parts show, actually, that they kind of highlighted this use case. You have this original steel design that you're seeing in the top left. And then, if you just take sort of the black metal part, right, and just take the existing design and convert it to composite, there was some marginal benefits there. But once we put it through our design optimization, you can see in the middle there, we're taking the build module and creating all these different 2D preforms. In the middle right there, we're combining them all, kind of pre-assembling it into the mold. And then in the fusion module, we go in and we press it all together with metal inserts, et cetera, and you get the finished part at the bottom. And when we did that, you really can get this 75% weight reduction relative to that original steel hinge. And, significantly better mechanical performance, not just equivalent, at a 50% reduced production cost. And this was on the order of 10,000 or so parts a year. We've done a similar program with Purdue that was highlighted actually at CAMX when we had our booth there, our first show in the US back in October. So we'll be, certainly doing more of that. We'll be at SAMPE in Seattle in April, and then the following week at JEC as well. So hopefully you guys will see more and more of us in our technology. But in this example here, with just about 10% of that whole part was actually continuous fiber and printed. The rest was a lot of this BMC compound we threw into the mold. And as such, with this hybrid approach, we're able to get 50% reduced production costs, 45% weight reduction. This is relative to aluminum, right, at 10,000 parts a year. So pretty compelling, cases here. And I think we have a SAMPE paper that was even published that we'll be presenting, or should be in the proceedings for Seattle. So our business model, you see our equipment, you see our process, but we don't necessarily try to just sell the machines to companies. At the same time, we're also not trying to become a parts supplier here. What we want to do is enable suppliers and OEMs to use AFT and make it a standardized process, in 5 years sort of time from now, right? And so the way we want to do that is we work with the customer up front to scope things out, and then ideally we kind of get this on average 6 month, we call it proof of concept project, feasibility discovery phase, whatever you want to call it, on the order of 50 to 100K, where we work on, think of it almost like a phase 1 SBIR in a way, right? And we find a candidate application that we think is really high value add and typically has a path to production, and is not just like pure R&D. So we like to work with them, kind of hold your hand and use our services, our engineering, manufacturing services, and our machines to make some of those prototypes and even some of that low rate initial production, like the first 100 and like the first 1,000. In fact, we recently had a case with Oris, a watchmaker out in Switzerland, where we did just that. And then as production ramps up, at that point, we'll transition the machines to our customers and allow them to take it into production from there on out, right? And so that's sort of the business model. And so we're looking for more and more partners to work with us and collaborate with good candidates, aluminum, steel, titanium parts that you can really try to lightweight, keep it without sacrificing performance, cost, any of that. That's what we're looking for, those types of applications. So if you have anything of interest, this is my contact information, pretty easy, assuming you can spell Konstantine with a K. As I like to tell people, there's no C in the Greek alphabet, so I spell mine with a K. But there's my email address. You can find me on LinkedIn, phone number, and like I said, we're located here in Lowell, Mass. So if you're ever in the area, please do reach out, and we'd love to. We have a nice showroom set up here. Actually, we have machines here as well. And like I said earlier, we're growing the team to support these projects with customers and ultimately, ship machines out to various suppliers. So at that point, I think at this point, it's my last slide. So I'm happy to take any questions.
Yeah, no, thanks, Konstantine. So if people have questions, please put them in the chat or go to the Q&A box. And so there is one in the Q&A box. And I think it was asked before you put the slide about which polymers you're using, but it's asking if you use thermoplastics or thermosets, and if so, which. So I guess the question I would have is do you, can you do this with thermosets as well? Because you did show a number of thermoplastics, and I'm sure that's not the complete range.
So it's an open material system for thermoplastics today. Can we ultimately do thermosets? I'm sure there's opportunities to do that. We're not currently, it's probably on our roadmap in 3-4 years out, I'd say. There's some additional complications associated with thermosets, backing paper, shelf life, all that stuff, right? That kind of plays into it all. But right now it's exclusively thermoplastics, but there are no real limitations on which thermoplastics, I'd say.
Okay. All the way up to PEEK.
Exactly. Yeah. We'll go polypropylene, polycarbonate, all the PA6, PA11, PA12, PPS, all the way up to PEEK, PEC, PAEK. Okay.
All right. Yeah, obviously PAEK is obviously coming on pretty strong these days. Yeah,
that's right. Yeah,
I know
exactly.
Arkema's got a new low melt version of that.
Yeah, exactly.
Yeah. So a question about how large of a part can you make?
So the build module is limited to about, I'd say roughly a foot, maybe 13 inches or so in one dimension, right? But what we can do, it's unique, the fusion module is bigger, right? So the fusion module is like, I want to say 16 or so inches squared in area. And so we've actually had a few of these where we've co-consolidated multiple preforms. So, in some of these seating applications or larger applications, we've taken two smaller preforms, brought them together in the fusion module and created, a larger part. So, and I can say we are working on a bigger fusion module as well to support, and build module to support even larger parts that should be out, I think 2024 timeframe, 25 timeframe.
Okay. Right. If somebody wanted to buy a machine, what's the lead time?
Lead time's probably on the order of a couple months. We have some in inventory out in Zurich right now. So it would probably take a couple months to get things, spooled up and shipped out. We can sell machines separately. So you may only want the build module, you may only want the fusion, or we could sell them as a set. And with that, there typically comes there's an annual subscription on the software. There's support involved as well. So, but typically right now, each machine is on the order of about 100K. And you can get the Fusion module for 100K, build module for 100K, or the full thing for just over 200K, right? Obviously, as a set. And like I said, it'd be about a couple month lead time.
Okay, and we're going to make this the last question is, what about PEI polymer, polyurethane, and what's the footprint of the machine? What are the power and other utility requirements?
Yeah, so PEI, yes. Neglected to mention that one as I went through my range of thermoplastics, but that's definitely right there in the middle. So we can absolutely do PEI. The footprint of the machine, the build module itself is, in the order of, 3 feet probably wide and maybe a couple of feet deep, right? So it doesn't really take up a lot of space. We put it on a cart. In fact, I might even have an image of this. Well, that doesn't really tell you much on the scale there.
Yeah. I mean,
but
certainly we've
yeah.
seen it on the show floor. There you go.
Yeah, exactly. So here we go. It's on the cart, and then the Fusion module is a little bit bigger. That one's about 7 feet in height, about 4 foot square footprint, and that's a little bit more. I mean, it's a press, right? So it's a little bit more of a beast for sure. Okay. Power requirements. Right now, it's all rated to EU power. We are definitely working on getting that to be automatic, and universal, right? So we don't need like transformers and stuff like that. But at the moment, it's all sort of rated to European specs.
Yeah. So is it like 240, 480? What?
Yeah, 240. I think the Fusion module might be 480.
Okay.
Oh yeah, that's right.
Okay. So there's a couple of the questions in the Q&A. Would you do me a favor and go in and answer those?
Absolutely.
Yeah, go to Q&A and then type your answer into those for those couple of.
All right. Thank you very much. Okay. I can stop sharing or
yes. Go ahead and stop sharing and we will move on to what I guess you have. So now Bryce, I want to introduce Bryce Anselmo, who's the Director of Product Management for Leighton Industries in California. Bryce, if you can go ahead and share and get started, we'll move on.
Yeah, thanks, Dale, for the intro there. Perfect. So sharing slides here. I'll get rolling. Leighton Advanced 3D Graphene Platform. We have multiple different application areas. Obviously, this forum here is on composites, so I'll spend time on that, but happy to take questions offline or not on some of these other application areas, specifically lithium sulfur batteries, different sensing elements, and coatings. Again, all enabled by the 3D graphene platform. So a little bit about Leighton, maybe before we get into the different materials. Mission statement here, taking 3D graphene into manufacturer-ready applications. So with that, to look at that differently is really, we're not just a material supplier, but we want to work with the end application platform and really engineer and architect our materials into that application to unlock whatever that performance criteria may or may not be. The company was founded in 2015, an inventor of the 3D graphene line, 3D graphene construct. Again, this is really a platform of materials. I'll talk about that in a little bit on what that means, but it's not just one material across the board. We're a global leader in 3D graphene IP. There's about over 300 patents granted or pending, and that IP stems all the way through the equipment that makes the material, the actual material, and then the material in application. So across the full breadth there. The headquarters that we have, you see a picture here on the left. We're located in San Jose, California. So for those familiar with the Bay Area, we're at the bottom of the Bay. But we do have a few facilities throughout the Bay Area, as well as in a couple other states as well, and a few satellite offices as well. So we are growing rapidly. The facility you see here on the left is a 55,000 square foot facility that we've built out over the last few years. And some of the highlights are really, this is the core of the manufacturing site for the 3D graphene currently. And we go from making the materials into the application labs, specifically, again, for this audience, composites, but we also have other application areas for the other products. Another notable within this facility here is really the pilot cell production line. It's actually in a dry room. And again, pilot cell being on the battery side of the product lines. We're over 200 employees. And in fact, I was just looking at this number and it seems to increase every week here. So we are growing rapidly and hiring. I'll put that shameless plug out there. If you haven't really heard of Lighten, even though we were founded in 2015, we were in stealth mode or so. So weren't very public with any information until about Q4 of 2021. So about a year and a half ago now. And that was really by design and a business choice to keep focused on supplying the customers that we had. And we've had history with the US government since the early days of the company and still do. So there's been some engagements there. We aren't only a government, businesses, but we are expanding out into commercial entities. And I'll talk about one of those here in just a moment. So what is the 3D graphene? I'm sure some of you on the call are familiar with graphene or different graphenes. So I'll take a little bit of time here to explain that. If you look at current graphene, a lot of them on the market or that have been as well. We get this all the time saying, oh, I tried graphene 10 years ago and maybe it didn't work or it didn't disperse, so we didn't see the performance gains, et cetera. I think we've come a long way as an industry in terms of advanced materials, really to understand the graphene content that's in there. So there might have only been a little bit of graphene in that bottle or that jar of materials. But what we've done here is really synthesize the material from a hydrocarbon source, and then we refer to it as a nano assembly. So actually at the molecular level, modify and manipulate the atoms to arrange in an orientation or a pattern that you can see here on the bottom left, just a few of those structures. Again, the engineered 3D structure really is an architect and designed for an end application. It's a highly pure system. So there's 4 nines pure or higher of graphene content. And really what the 3D graphene enables that, really a 2D material doesn't. If you look at a 2D material, you typically rely on just the edges. So maybe 1-2% of that full material surface area is allowed to react with a medium. So for example, plastic. But if you're able to modify and architect that to have, let's say, more edge sites or more reactivity on areas that were traditionally a basal plane without reactivity, then you can get a higher reactive sites, and you have a better, let's say, interfacial bond between the graphene and the host polymer, for example. So that's sort of one main difference. I did want to point out too, a lot of the graphenes on the marketplace are actually milled down from graphite. So you're relying on your source of graphite or the ability to, etch that down, whether it's mechanical, chemical, or both. And then you typically get a lot of those impurities as well as defects within those materials. Again, we nano assemble those from a pure hydrocarbon source. So what we do with the material and how we use that is, if you see here on the right-hand side, you have the 3D graphene fabrication. We then have a full metrology lab where we look at those materials and analyze those. So, some of your standard things like pore size distribution, Raman spectrum, et cetera. We also have our own TEM and SEM to look at these materials. And then what we do is once we're satisfied with that material spec, we then put that into the application app. So you see here composites relevant to the audience here. We have a small injection molder as well as a twin screw compounder. And then we have the ability actually with some of the IACMI partners, this consortium has been great actually for us to scale up to, we would call that maybe a pilot scale. And then we rely on the industrial scale, at least on our partners, our commercial partners at the moment. So we can do that under one roof, and then we do the testing as well. So we have all the mechanical, insutrons, et cetera, environmental chamber to do the testing. And then if we get the performance we like, of course, then that's where the customer receives it. If not, or there's an iteration cycle, then that continues. So it's really a flexible platform that's being engineered, architected, and optimized for that end use application. So maybe look at it a bit of a different way. We don't just take the material and throw it over the fence, but we really take the 3D graphene construct and tune that morphology, so modify and manipulate the 3D structure. But we also can add chemistry or functionalization, however we like to look at that. Functionalization really captures not only the surface chemistry, but the ability to, let's say, maybe have a coupling agent if that's needed for that end polymer system. And then that's where it goes into the application, as I mentioned. Composite sensor and battery is largely what we're focused on at the moment. So what do you get with the performance here? So Lightens Lighter, LYTR, is a trademark name that we have for our current solution and formulation within rotationally molded applications. That the rotomolding, for short, rotomolded properties really are utilizing polyethylene, various forms of polyethylene. And what we found working with some of our partners is really the ability to reduce the plastic or polymer by 50%. So you get a similar performance, but with 50% less of that plastic within the end system. What we've been tasked with a lot and here that the industry needs is really a stiffer polymer system. So what we've developed and engineered for is a flex modulus improvement, really as the driver for stiffness or criteria for stiffness as a screening mechanism. You'll see here the flex modulus in the middle, 177 KSI, based on the ASTM standard, is about a 40 to 50% improvement on stiffness over the base polymer system. Again, in application, rotomolded. For those that aren't familiar with rotomolding, you have a melt polymer that's in an oven that's rotationally molded, and then that product comes out. I'll show a couple pictures here on the next slide and one of the partners that we're working with on that to underscore that point. Not only do we have our material that adds stiffness, but the real criteria here is, if you look at some of the standard mechanics, typically some of these stronger or stiffer systems don't elongate, or maybe they become a bit brittle. But what we've really engineered for is to keep the elongation of the base polymer similar or the same, in fact, by also getting that stiffness. So for those that know polyethylenes, they're very, they can be very stretchable, 800-900%. You can even max out the tensile elongation. We're also able to do the same with the flex modulus improvement with this solution. So again, that's taken us time to really develop and understand that and how our formulation plays with the polymer from the interface of our material, the 3D graphene, into the plastic. This has also been third-party validated, so it's not just in our labs or in our customers' labs. We've went to a third-party validation to really get that data to ensure that the information and the data that we're getting is true. I'm not sure if these slides would be available, but the bottom here is a press release. It's linked to the solution. You can read a little bit more about it, but it's really just what I mentioned in a nutshell. It digs into it a little bit more. So here's one of our, I'll use this as a case study, rotomolding with Lightens material. So it's not only you get the stiffness improvement, there's always questions about, well, how does it mold, how does it fabricate, what do I need to do differently? Lighten is working with Pelican. You see some of their cases here. And again, these are rotationally molded cases. You'll see some metal inserts and inlays as well in here. But this is some of the feedback that we've gotten really from the technicians and fabricators of their products. The Lightens Lighter is a near drop-in. And that is they took out the material that they're currently using and put in our material, and they fabricated beautifully. And you see a stack of cases here on the right-hand side that we're utilizing for various testing. Of course, owing to the stiffness, the parts are stronger. They hold their form better. If you dig into what that means a little bit, the materials actually, when they're molded, they're able to come out of the mold actually even better than the base material that was being used. So sometimes you get some challenges with actually trying to get it, and you maybe need a crowbar to pull it out of the mold. But in fact, these came out of the mold beautifully. And then, of course, one of the big opportunities is lower material consumption. Again, if you're using 50% less plastic, not only do you use less per part, but then if it loads quicker, you also have the productivity gains across the board of less less material used, but also more parts made per hour, for example. And this is again on an industrial commercial scale. So they're, we've made, as you can see, a stack of cases, and in fact, there's quite a bit more that have been made to really screen some of this. So really key takeaways. This is more or less my last slide here. I did want to save some time for questions if there are. But in advanced materials and application engineering, so we at Lighten take our materials and love to design and architect and engineer those into end application, really demonstrating a 50% weight reduction potential on the polymer systems that we're using today. There's established 3D graphene solutions, again, in applications. So it's not just a material sitting on the shelf that we throw over the fence, but specifically designed for various different applications on the end product. I talked here today a lot about really just rotomold, just to give one, small example here in just a 20-minute window to this audience, but we really do have a lot of other composite developments underway that I would be happy to follow up with anybody that has any specific questions there on what we're doing in other product areas. But in the composite realm, we're probably at about another half dozen, a dozen different application areas that we're engineering and designing for today. So with that, thanks everybody for your time, and I want to thank IACMI and for setting this up. Really appreciate it.
Okay, so questions are rolling in, Bryce. Thank you for that presentation. So it's always good to stir people's imagination and ask questions. We'll start with the first one. What's the business model for use of your graphene and composites? Do you sell the graphene? Do you sell a compound solution? Do you do the compounding? What's the business model here?
Yeah, great question. So on the polymer itself, we have our material compounded into the polymer, and depending on how the end application would like that, it could be either in a master batch or in the final formulation. And then specifically for rotomold, those are actually ground into a powder. So we would supply either the powder or the pellet, depending on how that end customer would look at it. So if we look at thermoplastics, that's been the tried and true way for the business model. So maybe I'll stop there.
Okay. So question is, how is the dispersion achieved for rotomolding? Are the powders simply dry blended?
Yeah, so that one, we actually take our formulation, put it in on the twin screw compounder, so it gets compounded in. I think that question is probably related to a dry blend being like a pigmentation, where you get the pigment actually between the grain boundaries of the polymer. But our material is engineered into the plastic, so you have a better bonding, and then it's actually throughout the full system for maximum performance.
Okay, so on the Pelican case, how did the cost change correlating to the polymer weight change versus the cost of graphene? So you showed, obviously a much thinner wall, but what was the net effect on cost when you factor in the cost of the graphene?
Yeah, no. So if you have to actually maybe draw the box a little bit bigger than just a material differential versus performance. If you look at some of the productivity gains and some of the safety of users of the product, I think you start looking at a really compelling story, and in fact, it is a compelling story for that price for performance, but not only from just a pure material savings or an enhancement or a lighter product, but again, the productivity gains of the fabrication cycle. So that price for performance is on par.
Okay, so I guess the way to phrase it would be, lighter case for the same cost, overall finished cost, or was there a cost premium at the end of the day?
Yeah, I can't talk too much or speak on behalf of Pelican on what their sales model would be on selling it, but I would say if you look at the full encompassing of all the fabrication, it's been a compelling story for someone like Pelican to utilize this material from all the benefits that they've seen.
We'll take one more here, and then I'll ask you to go in and answer the rest of them.
Sure.
Q&A box, but type those in. So what's the typical loading in a composite part? I think this is always the question that comes along with graphene or any kind of fillers like this is people tout things like 0.1% or almost seemingly unrealistic in terms of physics. But what is a typical loading?
Yeah, I think so. The typical loadings are low, and I think someone as an industry or program to think about loading when you look at fiber dominated systems and how much fiber's in there and what that performance, how am I going to fabricate that, et cetera. And you're right. So there is some leverage on the industry to think, well, hey, if we can only put 0.1% in the system and get a performance gain, that's great. But it really comes back, ends up being on a performance side. So it's also not just the material itself. I do want to underscore that. But if you have some chemistry or coupling agent associated with that, it ends up being less relevant on exactly what the percent loading is because it's a full formulation really for that end application. But if to answer the question directly, it's a very low amount of light and 3D graphene in the product.
Okay, so there's about half a dozen more questions. We don't have time for them to go live. So if you'll just go in and type the answers to those, that would be greatly appreciated.
Thank you for the opportunity.
All right, thanks. All right, so we're going to move along to Joe Fox. He's a consultant in the industry, longtime industry participant, mainly in resins and other materials. And Joe also heads up IACMI's Infrastructure and Construction Working Group. So he's going to give a brief update on what that group does and some of the more recent successes it's had. So, Joe, over to you.
Great. Thank you very much, Dale. It's a pleasure to be here. And I'm going to give an overview of the INC Working Group, just a little bit about working groups in general. IACMI has 5 of them, and their mission is to focus on the techno-economic barriers to mass adoption of composites in partnership with similarly aligned organizations. So there are 5 of them. I'm going to tell you about this one. So a little bit about history. The INC Working Group was formed in October of 2020 when infrastructure became a new focus area for IACMI. It's been a very active working group. We have members representing the entire value chain that I've shown here. We've got material and equipment suppliers, composite fabricators, installers, designers, owners and operators, and typically, we have 40 to 50 people at our meetings. More than 80 people have actually opted in, and we're always looking for more downstream members at the end of this value chain. The co-facilitators are myself and John Unser from the Composite Applications Group, and our working group has held 10 meetings since it started, 8 virtual and 2 in person. So I'm going to talk about these key activities. I'm going to talk about collecting and disseminating information about infrastructure legislation and opportunities, putting together an INC strategy for IACMI, creating and funding R&D projects, and increasing awareness of FRP composites in the INC community. So motivation for forming the working group. Well, obviously, infrastructure is a very hot topic. The Infrastructure Investment Act, or the IIJA, or the infrastructure bill, was passed in November of 2021. As you can see from this graph, it talks about $1.2 trillion in investment over the next 5 years, and it invests in all 17 categories of the American Society of Civil Engineers report card. And as such, it represents the largest investment of its kind in our nation's infrastructure in our nation's history. So there's a great opportunity. There's also a very good fit with composites. In fact, there's an extremely good fit between FRP composites and our nation's infrastructure needs, both today and in the future. So you've got a good opportunity. You've got a very good fit. That's a good place to be. So in terms of collecting and disseminating information, we really try to answer these 2 questions. What's in the infrastructure bill, and what funding opportunities exist for infrastructure related R&D? Where is the money going to be spent, and where are opportunities for IACMI and its members? So this is the kind of information that we show to our members. We show about the different areas where money is going to be spent. We show how it's going to be spent. We show where it's going to be spent. And really, if you look at the infrastructure bill, there are really 2 big buckets of money. There are hundreds of billions of dollars, and that's billions, for construction projects to repair existing infrastructure like bridges and pipes and ports. And then there's also money for new infrastructure like EV charging stations. And again, you're talking hundreds of billions of dollars. And then there are also tens of billions of dollars for funding for R&D related to infrastructure. Billions, not millions. So we are interested in both of these buckets. I'm going to talk about this bucket a little bit later in my presentation. So let's talk about an infrastructure and construction strategy, because I said back in 2020, this was a new area for IACMI. And we talked about techno-economic barriers for all the working groups. These are the key barriers that are being addressed by the infrastructure and construction working group: cost competitiveness, education, lack of codes and specifications, sustainability, and performance issues. And here are the objectives for the INC working group. I'm not going to read this slide to you, but the objectives really tie very closely to the barriers that I talked about on the previous slide: life cycle cost, awareness, modeling and simulation tools, and R&D projects. And I really want to spend a few minutes talking more about creating, managing, and publicizing industry-led demonstration projects and research projects. So the working group has really adopted what I call a parallel path strategy for R&D projects, in that simultaneously we are trying to develop a list of potential projects and simultaneously trying to identify and secure funding for those projects. The rationale is to have projects that are already well-defined once funding becomes available. And so let's talk a little bit about identifying and securing funding, because the working group has formed a funding subcommittee to identify sources of funding. And they have really looked for funding from two federal entities: the Department of Transportation, looking for funding for infrastructure-focused projects, and the Department of Energy for construction-focused projects. And that strategy, I'll explain it a little bit more on this slide. If you look at the infrastructure-related activities of the working group, they really line up very well with the Department of Transportation, things like bridges and ports and inland waterways. And you're looking for matches in terms of resiliency and life cycle cost analysis and ease of installation. And then on the construction side, you have the Department of Energy really looking at buildings and homes, and they're interested in decarbonization and industrialized construction. And all of these areas match up very well with IACMI's capabilities and interests. So let me say just a little bit more about the kind of information that we collect as a working group. Let's focus on the DOT, and again, resiliency and durability. And over the last several months, we have collected information about the numerous grant opportunities available from the DOT for infrastructure. And this really is an alphabet soup of acronyms, but we have information on all of these different grant programs. Similarly, on the DOE side, which is focused on construction of buildings and homes and decarbonization and industrialized construction, they have multiple offices: AAMTO, BTO, IEDO, that all provide funding opportunities for this kind of activity. And there's also a new joint office of energy and transportation that is co-funded by the DOE and the DOT. So I've talked about funding R&D projects. Let's talk about creating R&D projects. So the working group really has a process for pitching R&D projects to the subcommittee or to the entire working group, and then the working group votes. We have a process where we listen and then we vote. And to this point in time, 10 projects have been submitted for consideration by the working group, and all 10 are listed here. I'm actually going to talk very briefly about the 4 that I've highlighted here. And what's nice about these projects is once they are launched, once they get going, you've got a very large working group breaking down into smaller working groups or subcommittees, and that's where things really begin to happen. So I'm going to talk about these 4 very briefly. I'll start with what we call the Trimer project, which involves the development of fire-resistant resins for infrastructure and construction applications. The project team consists here of Orenco and Trimer Technologies. Trimer Technologies is the resin supplier. Orenco is the composite fabricator. And the scope of the project really involves preparation of samples and then conducting of a series of fire-resistant tests with one of Trimer's resins. Samples and assemblies are fabricated by Orenco. And here are the tests that are being conducted at either the University of Dayton Research Institute, UDRI, or Southwest Research Institute, SWRI. And I'll just point out that this was the first project to receive IACMI Resource Pool funding last year. The Resource Pool funding is a slice of the membership fees that is taken and devoted to supporting research projects. Just a little bit about what Orenco is interested in. There's a lot of applications where fire resistance is important. They're highlighting the ones that I've shown here, the data centers, the heliports and vertiports, and small industrial buildings. And again, a little bit about the mechanics of the project. Trimer provides the infusion resin and process know-how. Orenco fabricates the samples for testing. The best way to describe them is web stiffened and cord panels. And then the fire testing is conducted at UDRI and SWRI. Here are pictures of the cone calorimetry samples that have already been tested at UDRI. And here is a sample of an E84 cord panel that is ready for testing at SWRI. And that's really the next step for that project. Let's move to the second project, recycling of wind turbine blades into infrastructure and construction applications. This is really important to IACMI members like TPI, which are getting ready to decommission thousands of wind turbine blades and want to find something to do with them other than put them into a landfill. Well, the working group has identified recycling technology from two companies, River's Edge Composite, which is a boat fabricator in Florida, and GreenTex, which is a startup company in South Carolina. And their technology involves taking the blades and grinding them or shredding them, and then compression molding them with a binder into panels like the ones that are shown here. And really, I have to give a kudos to Steve Nolette from TPI, who has really been spearheading this project. So what has Steve done to this point? Well, they've actually taken shredded TPI blades and successfully prepared 2-foot by 2-foot lab samples. They've identified a cost-effective phenolic binder for the process, and they've created panels like the one shown here, which could be replacements for things like oriented strand board and plywood. I mentioned they've made lab samples. The next step for this project is to do compression molding of large 4-foot by 8-foot samples with this big compression press at TPI. Third project I want to talk about is predicting the lifetimes of composites in INC applications. And this project is still in the definition stage. It started as a project to enable state DOTs to better conduct benefit cost analysis and life cycle cost analysis with composites. And here are some of the documents that are relevant to the project. This is a BCA guidance document that was issued from the DOT last year. This is a life cycle cost analysis for what's known as the Halls River Bridge in Florida. It's probably the most comprehensive LCA and LCCA for FRP in infrastructure. And here's a benefit cost analysis that was actually conducted by my co-facilitator, John Unser, and a team for the Morgan County Bridge in Tennessee. This is how the project started. This was the initial vision, and then it morphed. And the reason it morphed is because of a very important meeting that we had in November with what we call a DOT sounding board. We assembled a team of 7 DOT representatives from 5 different states all around the United States to obtain the voice of the customer. Basically, we gave them our vision for the project, and then we listened. We listened to their priorities. And they told us, yes, we're interested in benefit cost analysis, but we're more interested in life cycle cost analysis. But what we really need, a critical need, is we need lifetime durability data. We need the ability to predict the lifetimes. They want to increase their comfort level with how long FRP bridges will last. And if you provide them with this lifetime durability data, it will give them data that would make these LCCAs more accurate and more meaningful. And so the good news is that this represents an excellent opportunity for IACMI to respond to this high priority need, because we can do things like accelerated testing of composites and simulation and modeling to extrapolate and predict lifetimes. So the project team is in the midst of refocusing the project. And there's more good news. The DOTs want to stay involved. All 5 states want quarterly updates. The next one will be planned for March. Last project I want to talk about is decarbonization with FRP composites. And like infrastructure, decarbonization is another hot topic. Seems everyone wants to lower embodied carbon and carbon dioxide emissions. Here's the list of priorities for the Department of Energy's Office of Energy Efficiency and Renewable Energy. You see here, reducing the carbon footprint of buildings. And this is the title slide of a presentation that was given by Turner Construction's Chief Sustainability Officer. They were talking about their strategy for net zero and how they were looking for building materials with low embodied carbon. So again, here's another project that's still fairly new. It's in the formative stage, but what do we want to do? We want to create more stories like the LCA for the Halls River Bridge, because it has shown that carbon dioxide emissions are 26% lower with FRP than with steel. We want to generate more stories like that. We also want to get data for FRP composites into embodied carbon databases like this one from the Carbon Leadership Forum. It contains very useful embodied carbon data for building materials like concrete and steel and aluminum, but there is no FRP data in that database. We want to change that. And we want to work with IACMI, which has initiated their Climate Impacts Project, and with an organization called the Advanced Building Construction Collaborative to collect the data and then spread the word throughout the INC community. The last thing I want to talk about is increasing awareness of FRP composites in the INC community. Last April, 4 members of the working group collaborated with ASCE to put on a 90-minute webinar entitled An Introduction to Designing with Fiber-Reinforced Polymer Composites, designed for civil and environmental engineers. And we really assembled an all-star list of professors. Dayakar Peñamato from the University of Tennessee started off with basic mechanics and properties of composites. He was followed by Francisco de Caso from the University of Miami, who talked about designing with rebar. And then Bill Davids from University of Maine finished up with talking about FRP girders. And they all did an outstanding job. We have a very good story to tell, but we really need to take every opportunity we can to educate the civil and environmental engineering community about FRP composites. So that really summarizes or completes my overview. If you're interested in joining the working group, you can send me an email at the address that has shown there. And that concludes my presentation, and I'll be happy to answer any questions.
All right, thanks, Joe. Yeah, we're getting close to the end of the hour, and there's nothing specific other than, yeah, somebody was just wants to make sure they can get contacts for each speaker, and copies of the presentation to go over with their team. I'll work with Kim on that. You know, the person asked that question, if you'll email Kim Hoodin, that's KHOODIN at IACMI.org, she can let you know which presenters will be willing to make their presentations available to you, and then she can email those to you. So it's K Hoodin, you know, and maybe she can stick her address in the chat. Or I'll just put it in the Q&A right here. And you know, so if you look in the chat, you can see her address. And so all, as I mentioned before, all of these are being recorded and then will be available on the IACMI website. So we'll at least have the live version. I believe every speaker put their contact information in that. So those should be up within the next couple of days. And then just reach out to us and we'll work to get you copies of any presentation that you want. Okay. Well, it's 1 o'clock. So we're at the end of the period. Our next Innovation Insights will be on Monday, February 27th, so 4 weeks from today. Be on the lookout for the lineup for those speakers here in the next week or so. So Thank you again for joining us, and we will see you in 4 weeks. Thank you.
Thanks, Dale.